All right. So I want to start this discussion. What we're going to really talk about in this particular lesson is ions and the lattice energy associated with those ions attracting each other. We're going to talk about some trends when it comes to ionic size and a few other things. But I just want you to be aware that when I start talking about this, when we discuss ionic compounds, we're almost always referring to the solid state. Okay? We're not talking about liquid state, gaseous state. We're predominantly going to be talking about the solid state. And the solid state is the result of a large amount of positive and negative ions being attracted to each other. And in that structure is going to be the shape, or it's going to be arranged in a way that maximizes the attractive forces of those ions and minimizes the repulsion forces of those ions. Does that make sense? You guys remember me pulling out that cube-looking thing with the, you know what I'm talking about, right? Yeah. The white and black spherical objects. I'll take my foot out of my mouth. Okay? No? You don't remember?
It was sitting out.
Yeah, it was been sitting out for like a week or two. Now that one shows a 1-to-1 ion ratio, what the structure would look like. Now if you had a 2-to-1 or a 3-to-1 or even a 2-to-3 ratio, the structure is going to look differently, because you would have to arrange them differently to maximize your attractive forces and minimize your repulsion forces. Okay? Big in there? All right? So, just making you guys aware that when we're talking about ionic compounds, we're talking about them in their solid state. So, for example, when Mg bonds with O, you got your Mg2 plus ions and your O2 minus ions. This is stable, but this in the gaseous state is not stable. In fact, it would rather be in its lone neutral atom state than in the ion gaseous form. It's more stable for it to be in its lone net neutral atom form than to be in its gaseous ionic state, or ion state. Okay? So when we're talking about ion compounds, we're going to assume, I mean, you probably already assume that whenever we talk about it, we're talking about the solid state, but just making sure that we're aware of that. Now, you guys already know this, but typically the group 1 metals are going to lose an electron, group 2 are going to lose 2, group 3 are going to lose 4, group 7 is going to gain 1, and 2, and so forth. There are a few exceptions on here, and they involve the transition metals, where they can actually do bond multiple ways. I don't know if you guys have this anywhere in your notes. It doesn't appear that you have them in your notes, but in your book you'll see it. Tin can actually have a 2+ oxidation number or a 4+ oxidation number. I don't know if you guys realize that they show them there. I don't know if you can do that. All of group 1, 1+, 1+, 1+, 1+, 1+, 2+, 2+, 2+, 2+. When we start getting into these, that's when they bond covalently, and that's why you see all these multiple oxidation numbers, which we'll deal with once we get to like chapter 19 in the book. But that's a ways away when we start talking about oxidation reduction reactions. But just making you aware that there are some guys that bond plumbum or lead also acts like that, thallium, and a few other guys. Okay, so let's talk about size of ions. Your book talks about how there is quite a bit of disagreement about like ionic sizes, like how big ions are going to be in a variety of different sources. Your book says it's kind of like it's debated, essentially. And so we're going to kind of focus more on the trends and the big picture and be less concerned with the absolute ion size, like what actually it has to be. We're more focused on the trend. I think that's going to be suitable for what we're going to be going after at this point. And this first trend should be, it's one you've seen before in regular chemistry, but it also is fairly easy to explain. It says cations are smaller than the neutral atoms, and anions are larger than their neutral atoms. And it kind of tells you why, but you guys should probably already be familiar with this. Okay, cations, they gain or lose electrons? Lose, okay? Well, if you're not touching the protons and you lose an electron, you have the same amount of protons pulling on less electrons. It's going to make the size of that particular cation smaller. Right? Make sense? Okay? An anion is one that gains an electron, and so therefore you have the same amount of protons, but you have another electron that they have to pull, and so you have a slightly bigger cloud. Okay? It's like taking that force and distributing it over more electrons. Okay? It's not going to be quite as strong of a pull. Make sense? I don't think there's too much that I need to probably discuss about that. Makes pretty logical sense. Next thing we're going to talk about, isoelectric ions. Okay? These are a group of ions that all have the same number of electrons. Do they have the same number of protons?
Not necessarily.
No, they're not going to have the same number of protons. And that's actually how we're going to determine the size of these guys. So I'm going to give you an isoelectric series here. So it says that an isoelectric ion or an isoelectric series is going to all contain the same number of electrons. So let's try to figure this out. How many electrons does neutral oxygen have? Okay. If the gain 2, it has. How many electrons does neutral fluorine have? If the gain's 1, it has. Are you seeing the trend here? They all should have 10 electrons. So forth. So magnesium has 12. Lost 2, they're all going to have an electron configuration of which element up here? Yeah. Okay? So isoelectric ions are a series of ions that all have the same electron configuration as one of these noble gases. Okay? So if I were to try to figure out the size of an isoelectric ion series, what would I be looking at to determine which one would be the biggest and which one would be the smallest if they all have the same number of electrons?
One of the most smallest.
Yep. Okay, so let's identify protons. We have 8 protons, 9 protons, 11 protons, 12 protons, 13 protons. All the same number of electrons. So which one was going to be the smallest radius? Why?
Because of the highest positive charge.
Yeah. They all have the same number of electrons, so the one that's going to have the smallest radius is going to be the one with the most protons that can pull those electrons towards itself, the greatest. And then?
And magnesium. Oh.
Alright, once you have your isoelectric series in its order, once you know which one's the largest or which one's the smallest, you have your trend, if that makes sense. So what you have is the smallest radius going towards the biggest radius. Okay, so then you need to know about isoelectric ions. Are they going to all have the same number of electrons? And I could do that with like that group, and that group, and that group, and so forth. Okay? All the same number of electrons, but different number of protons. So when you're trying to figure out radius, you're looking at the what? Protons. Okay? So I want you guys to do this one. Please identify or arrange these guys in order of decreasing size. The most positive charge is probably also going to be the
Yeah.
one that has the most protons.
Yeah.
Yeah.
So
You could look at you could look at the one that has the highest positive charge is going to be the one with the smallest radius. That's fine.
it's faster than,
Okay, so which one is going to be your smallest? Well, actually, it's going in decreasing order. So which one's going to be your largest? SE is going to be your largest. Did you just say that wrong, or did you mess that up? Decreasing side would be from biggest to smallest. Okay, so selenium 2 minus, and then your smallest is going to be strontium 2 plus. And then just follow the charges in between. We should be good at that. I'm assuming that makes sense? You yell at me again. I've been teaching this for quite some time, so it might seem to make intuitively more sense to me because I've been doing it for a long time. You need to tell me. It's your responsibility to tell me, hey, I'm not quite understanding this one thing. Okay? Sometimes I feel like there's a squirrel in the room.
chewing on the desks.
No. Students can't focus.
Oh.
Like a dog when they see a squirrel. Alright. So just look at the largest ion here. So one of these is not an isoelectric series, but that's okay. I think you can use just your typical radius trying to figure this out. You done, Grant? Done? Right, which one of these is going to be the largest ion? Why? Yeah, I mean they're all in group 1, and even if they all lost 1 electron, they're just going to act like their noble gas counterpart. And so we're talking increasing energy levels is going to give you your biggest size as you go top to bottom. Okay, and then which one is going to be the largest in this case? Which one? All right. All right, lattice energy. This is where we're going to end here. Okay, so what lattice energy is I know it seems kind of wordy, but it's the change in energy that takes place when separate gaseous ions go to form the solid ionic compound. So that would be like the Mg2 plus and O2 minus actually forming the solid compound. And you can imagine going from its gaseous ions to its solid compound is going to be giving off a whole load of energy. Okay? Not only are you going from a gaseous state to a solid state, but you're also having the charges play a big part in their attractive forces and the low energy that they gain or they get. So let's just we're going to look at how NIF works here, and then we'll get to the actual equation here. We're going to break this down step by step, and if you want to follow in your book as well, it's on page, I don't know. 355. I kind of have like a nice little flow chart there that might help you a little bit. Okay, so here's our overall balance equation going from lithium and fluorine to the compound LiF as a solid. Okay, what this is showing you is lithium's natural occurring state is going to be the solid lithium atoms, and fluorine's naturally occurring state is in diatomic gaseous fluorine, right? At room temperature, fluorine is a what? Gas. At room temperature, lithium is a solid. So in its natural state, this is what you're going to see. So for us to get to this, I've got to do quite a bit of things over to these guys. Okay, there's 5 steps here. The very first thing, we're gonna kind of walk through each of these steps, just kind of talk about what's actually happening here. All right, so lithium as a solid needs to go lithium in the gaseous phase. All right, so if we're talking about the energy associated with this, or your change in H, do you think this is going to be a positive number or a negative number? Positive. Why?
It's taking energy.
It's gaining energy. Okay, so it's about 161 kilojoules per mole. Set up my desk, please. Okay. Next step. Lithium as a gas becoming lithium plus and giving off an electron. All right, let me ask you this. Is this going to require energy, or is this going to give off energy?
Giving off energy. In form of electron. It takes energy to say that far. I don't know. So it takes more energy.
Remember ionization energy? The amount of energy needed to remove an electron? That takes energy. We're talking about ionization energy, right? And remember that table that we had that showed the first ionization energy and the second ionization energy and the third, and how once you removed a core electron, it was a huge jump. Do you remember that? Yes? No? Maybe so? Okay? Third thing here. So what this does is allows me to have, well, this is gas here. Allows me to have my gaseous lithium ion that we need to form LiF. Okay? Then I have to take the fluorine molecule and I have to break it down into gas here. I have to break it down into just a fluorine, one fluorine, non-diatomic. So let me ask you, going from diatomic fluorine to non-diatomic fluorine, do you think that's more stable or less stable? Less stable. Naturally, fluorine's diatomic because it's more stable in its diatomic form. So this is also going to be a huge increase, not huge, but an increase in energy. You have to divide by 2 because of the coefficients, but that's not huge deal. Fourth, we got to take that fluorine as a gas, and I'm going to give it an electron. Now the question is giving fluorine, neutral fluorine, an electron to become a fluorine ion, is that going to make it more stable or less stable?
How do you know? More stable because it's becoming the
It's going to get an octet. So actually, in this situation, this is more stable than this, so my change in H should be what? Positive or negative? Negative. So what we have here, ionization energy. What we have here, we know it's going to be an increase in energy because it's going to the gaseous form. Here I know F2 is more stable because it's naturally in diatomic, and if I break that apart, it's going to become less stable, positive. Here I'm gaining an electron. To have it a stable 8 octet is going to give off energy. Okay, then the last step is the one we want to spend some time focusing on. The last step is the lattice energy. Because by definition, we said lattice energy is the energy given off when going from gaseous ions to solid form. So we have gaseous lithium ion and gaseous fluorine ion that are going to form our solid. And this lattice energy is a huge dumping of energy. If I take all that, add it together, is this more stable than this?
Yeah.
From an energy standpoint, it is. And it makes sense why typically you're going to find them in this form if they can all make it happen than being in this form. Now, I do want to finish with this. Note that the energy released in giving fluorine an electron and the energy required to take an electron away from lithium means that I cannot just go straight from here, from this electron that's gained, or that's taken here, cannot just be, we don't have enough energy to take the electron from lithium. The energy given off when fluorine becomes stable is not enough to actually take the electron away from lithium. And so the dominating factor here is the lattice energy. It's the two charges allowing them to be attracted to form that ionic bond. That's the dominating force here. Okay? The energy given off to make fluorine stable is not enough to remove the electron away from lithium. Are you seeing it? Okay? It would take 520 kilojoules to remove the electron from lithium, and if fluorine would be able to do that, it would have to be greater. Want to finish? Oh. Yeah, I had a Betty. Sorry. Yeah. Sorry. I do it every time. Last thing I do want to talk about. I know you guys need to go. There's an equation that talks about lattice, or that allows us to find lattice energy. Okay, I just want to specifically point out what these variables are. Okay, this is R, this is distance. Do you have this in your notes?
I have the equation, not what it means.
Okay, distance between ions, and that is charge of your ions. Okay, so there are two things that are going to, that the lattice energy increases with. Okay? Lattice energy will increase in two situations. Any idea what those situations are looking at the equation? Decreasing distance and increasing charge.
What's the K? Constant?
Yeah, it's a constant. Does it not have it up there? My guess is it will have to be a constant that they will give you for the specific situation. Does this make sense? The bigger the charge, the stronger it's going to be held together, and thus the more energy, lattice energy you'll have or you'll be releasing, right? Does that make sense, everybody? And the closer the nucleuses are, the stronger it's going to be held. Remember, stronger held means more stable, which means more energy releasing. Okay? So lattice energy is the energy released when an ionic solid is formed.